In this chapter, we will focus on the structures of atoms. Let's first review the discovery of electron. The atomic theory is the scientific theory that matter is composed of particles called atoms. It traces its origins to an ancient philosophical tradition known as atomism. The word atom, meaning uncuttable, was coined by Greek philosophers. Democritus taught that atoms were infinite in number, uncreated, and eternal, and that the qualities of an object result from the kind of atoms that compose it. You can think about this using an analogy. The qualities of a dune result from the kind of sands that compose it. Similarly, the characters of a nation result from the kind of people that compose it. In the early 1800s, John Dalton noticed from his and others' experiments that each chemical element is ultimately made up of tiny indivisible particles of consistent weight. Dalton's law of multiple proportion states that, if the same two elements can be combined to form a number of different compounds, then the ratios of the masses of the two elements in their various compounds will be represented by small whole numbers. For example, Dalton identified two oxides of tin. One is a gray powder in which for every 100 parts of tin there is 13.5 parts of oxygen. The other oxide is a white powder in which for every 100 parts of tin there is 27 parts of oxygen. 13.5 and 27 form a ratio of 1 to 2. These oxides are today known as tin 2 oxide and tin 4 oxide respectively. Amedeo Avogadro had proposed that equal volumes of any two gases, at equal temperature and pressure, contain equal numbers of molecules. For instance, since 2 liters of hydrogen will react with just 1 liter of oxygen to produce 2 liters of water vapor at constant pressure and temperature, it meant a single oxygen molecule splits in two to form 2 particles of water. Thus, Avogadro was able to offer more accurate estimates of the atomic mass of oxygen and various other elements, and made a clear distinction between molecules and atoms. Robert Brown observed that dust particles inside pollen grains floating in water constantly jiggled about for no apparent reason. Albert Einstein theorized that this Brownian motion was caused by the water molecules continuously knocking the grains about, and developed a hypothetical mathematical model to describe it. This model was validated experimentally, thus providing additional validation for particle theory, and by extension atomic theory. Ancient Greek, Roman, and Arabic naturalists and physicians reported shocks from electric fish, like electric eels. Ancient cultures around the Mediterranean knew that certain objects, such as rods of amber, could be rubbed with cat's fur to attract light objects like feathers. Scientists in the 18th century eventually developed the concept of electric charge. There are 2 types of charge, positive and negative. Like charges repel one another, whilst opposite charges attract. When 2 bodies are rubbed together, charge can be transferred from one to the other. Thus, when amber is rubbed with fur, there is transfer of charge such that the amber acquires a negative charge, and the fur an equal positive charge. The word electricity derives from the New Latin and ultimately ancient Greek word meaning amber. Michael Faraday reported that the mass of elements deposited at an electrode is directly proportional to the charge. It is known as the Faraday's first law of electrolysis. For example, when an electrolyte with copper ion is electrolyzed, the element copper is deposited at the cathode, and the mass of deposited copper is proportional to the charge passing through the circuit, which is equal to the integral of current with respect to time. Faraday's first law of electrolysis suggests that matters and electricity are related to each other. This painting shows Alessandro Volta explains the principle of the electric column to Napoleon Bonaparte in 1801. This electric column is known as Voltaic pile today, which was the first electrical battery that could continuously provide an electric current to a circuit. A schematic diagram of a copper-zinc Voltaic pile is shown here. In each element, a copper disc and a zinc disc are separated by cardboard soaked in salt water, the electrolyte. The elements are piled in series, so that the overall voltage is the sum of them. In the Voltaic pile, electricity is produced by matters. It confirms the relationship between matter and electricity. Atoms were thought to be the smallest possible division of matter until work on cathode rays in discharge tube. A gas-filled discharge tube is an arrangement of electrodes in a gas within an insulating, temperature-resistant envelope, usually glass. When most air was sucked out to a pressure of around 100 Pascal and a high voltage around 10 to 100 kilovolts was applied between two metal electrodes, a glow with its beginning at the cathode, negative electrode, and its end at the anode, positive electrode, filled the tube. This phenomenon is called glow discharge. When the tube was evacuated to a lower pressure, below 0.1 Pascal, the glass at the anode end of the tube began to glow with a mechanism known as fluorescence. It suggested that a ray came from the cathode. The glow of glass could be made to shift by applying magnetic field. With the arrangement shown in the figure, the ray was shifted downward. It suggested that the ray is negatively charged. This phenomenon was first observed by Julius Plucker, and the ray was named by Eugen Goldstein cathode ray. At this time, atoms were the smallest particles known, and were believed to be indivisible. What carried electric currents was a mystery. The substance in the cathode ray was later named electrons, after particles postulated by George Johnstone Stoney. The mystery was resolved in 1897 when Sir Joseph John Thomson measured the mass-to-charge ratio of electron, showing they were made of particles. A photo and a scheme of his apparatus are shown here. In his experiment, the electron was first energized from rest by a voltage, U. The final kinetic energy of an electron is equal to the electric field work done to it. Here, m, v and q are the mass, velocity, and charge of an electron, respectively. Then, the speed of electron can be calculated. The electron then passed between two parallel aluminum plates, which produced an electric field between them when they were connected to a battery. Electrical deflection of electron was observed, which reassured that electron is negatively charged. Thomson then added a magnetic field perpendicular to the electric field. By adjusting the electric field strength and the magnetic field strength, he could make the cathode ray to travel in a straight line. Thus, the velocity of the electron, the electric field and the magnetic field are perpendicular to each other. Meanwhile, the electric force balanced the Lorentz force. The electric force is the product of the charge of electron and the electric field strength. The Lorentz force is the product of the charge and the speed of electron, and the magnetic flux density. By inserting the speed of the electron calculated before, Thomson could find the charge-to-mass ratio of an electron. Pay attention that charge-to-mass ratio is a property of particles. Therefore, finding the charge-to-mass ratio of electron showed electrons are particles. Significantly, the electrons from every cathode yielded the same charge-to-mass ratio. Thus, all the electrons are identical. Meanwhile, the charge-to-mass ratio of electron is 1,800 times greater than the lightest ion, hydrogen ion. Therefore, electrons are not charged atoms but subatomic particles. Thomson also estimated mass of electron by other experiment, but the results could not clarify if charge is continuous variable or discrete values. In 1910, Robert Millikan succeeded in precisely determining the magnitude of the elementary electric charge by the oil drop experiment. Millikan's apparatus incorporated a parallel pair of horizontal metal plates. By applying a voltage across the plates, a uniform electric field was created in the space between them. A fine mist of oil droplets was sprayed into a chamber above the plates. Some oil drops became electrically charged through friction with the nozzle as they were sprayed. Because the droplets were charged, when they entered the space between the plates, they could be made to rise and fall by changing the voltage across the plates, which determined the electric field strength between them. The velocity of the droplet can be measured with a microscope. The droplet very quickly reaches a terminal velocity because of friction with the air in the chamber. If so, the gravitational force, Coulomb force, and air drag are in equilibrium. The gravitational force is the product of the droplet's volume, density, and gravitational constant. The electric force is the product of electric field strength and the charge. The drag force acting on the droplet can be worked out using Stokes' law. It is the product of 6 pi, the radius and the velocity of the droplet and the viscosity of air. This equation has two unknowns, the radius and the charge of the droplet. One conceivable way to work out the charge would be to first turn the electric field off. Then, the gravitational force and drag must cancel one another out. This equation has only one unknown, the radius. Thus, the radius can be calculated. Then, adjust the electric field strength until the oil drop remains steady. The gravitational force and electric force must cancel one another out. Since the radius has been worked out, the charge can be calculated. By repeating the experiment for many droplets, Millikan confirmed that the charges were all small integer multiples of a certain base value. He proposed that this was the magnitude of the negative charge of a single electron. That is, Q is equal to minus ZE. Here, Z is a positive integer, that is, 1, 2, 3, etc. E is called the elementary charge. The charge of an electron is minus E. The currently accepted value of elementary charge is 1.60217663 times 10 to minus 19 coulomb. Furthermore, the mass of electron can be calculated from its charge and charge to mass ratio.